Welcome back. Today we're going to be going over lesson 2.6, multiplication and division properties in this geometry course. If you haven't watched 2.5 already, I recommend you do so, but I don't want to waste any of your time, so let's get into it. Okay, so first things first, right? Let's just review trisection and bisection, I guess, because those will be important for us to understand how these properties work. So here we have B, C, F, and G are trisection points, right? So those are our trisection points, and they tell us that AB, the measure of AB and EF are both equal to 3, right? What can we say about AD and EH? So the entire segment. Um, well, think about it, right? If we know that AB is 3, and we also know that B and C are trisection points, remember that trisection points to divide a segment into 3 equal parts. So that means if this is 3, so are these, right? And likewise, the same for this segment here, right? These are also 3 because of that trisection concept. So because of that, we can say that AD is 9, right? And EH is 9. And therefore, those are also equal, right? So again, because we know that these are trisection points and we know that AB equals EF, well, we can make the conclusion that um, any multiple of A, B, or EF, right? So it could also be, AC or EG that are equal. It can also be, of course, AD and EH that are equal, right? So that's where the multiplication property kind of emerges from. Similar thing with angles, right? If you have these two angles and they tell you that the rays in purple are angle bisectors, um, they'll also tell you that JKO and NPS both are equal measures, 25 degrees. Once again, if these are 25, because this ray is a bisector, that means it divides it into two congruent angles, and therefore that's also 25. Similar logic, right? So again, right, we can conclude that the overall angles are equal to each other because we know that they're bisectors and we know that a part of the entire angle are equal. Parts of the entire angle are equal to each other. So this is again where the multiplication property comes in, right? Make sure you know this one, pretty important. This theorem. If segments or angles are congruent, they're like multiples are congruent, right? So again, right, if B and Y are midpoints, right, and we're given that AB is congruent to XY, well, we can make a conclusion that AC is congruent to XZ, right? So these entire segments are equal to each other. Um, Once again, because, right, AB and XY, right, that's the F part, those are congruent. Um, the multiples are going to be congruent, right? Which means, again, the entire thing is going to be congruent, right? The reason it says like multiples, well, that like part, um, you have to first know that there's going to be like a midpoint bisection or trisection involved, right? You can't use this theorem if there is nothing like that, right? Second, it says the like multiples are congruent. Well, yeah, that makes sense, right? AC is 2 times AB, right? So that's a multiple, right? XZ is 2 times XY. So once again, that's why it says they're like multiples are congruent. And once again, I put like an analogy here to like a mathematical equation. If A equals B, well, of course, 3 times A would equal 3 times B, right? So once again, if you think of this as A, well, that's going to be 2A. If you think of this as B, the entire thing is going to be um, 2B, right? So of course, if A equals B, 2A equals 2B. Okay, division. Same thing, kind of in reverse, right? If segments or angles are congruent, they're like divisions are congruent. So generally, it's just the exact reverse, right? So let's actually start with the mathematical way. If A equals B, well, of course, if you divide those by 3, they're going to be equal to each other, right? So now what's different is that we're starting with a bigger figure, right? So we're actually starting with the fact that AD is congruent to WZ. So the entire segment is congruent, right? Instead of starting with the part. We're also given, of course, that these points here are trisection points, which is really important, right? So therefore, you can make a lot of conclusions here, but for the sake of this problem, you can say that AB is congruent to WX, right? Once again, there has to be some sort of trisection, bisection, midpoints involved, right? You can't use these properties if that's not established or given in the problem. So, and again, if that doesn't make sense, right? Let's say that AD was like 10, and so was WZ, right? And these are trisection points. So if you divide by 3, well, this would be like 3.3, right? These will all be like around 3.3. Same thing for these ones. So therefore, of course, these would have to be equal, these would have to be equal, right? So once again, same thing as multiplication, just in reverse. Okay, so I kind of want to like go over when you would kind of use these, right? So again, first thing, right? It's a good sign you're going to use these properties if there is a double use of the word midpoint or trisect or bisect, right? The reason I'm saying double use, well, look at all the problems they've done, right? Here, you're told that, for example, BC, B is a trisection point, C is a trisection point, right? So are X and Y. So those are like multiple uses of the word trisection. Same thing. We're given that B is a midpoint, Y is a midpoint. So that's multiple uses of midpoint. So once again, look for that double use. Then the multiplication property is used when the segments or angles in the conclusion are greater, right? I kind of was talking about that earlier, right? You start with a smaller specific part of a segment or angle and you expand it to the entire thing, right? Um, Same thing, right? For division, you start with a bigger, uh, like figure that's congruent, bigger fingers that are congruent to each other, and you make conclusions about smaller parts of those figures. So once again, division is used when the segments or angles are smaller than the given information. A lot of the times you're going to mix up multiplication and division with addition and subtraction. The key difference is, I know I mentioned it earlier in the video, or earlier in another lesson, at the actual last lesson, that you use addition when you have bigger things to prove, and you use subtraction when you have smaller things to prove. Um, that is also really similar to this, but the only difference is that multiplication and division properties, they have the word midpoint, trisect, bisect, right? So again, that's a key thing. This is a really important thing to have in the problem. All right, let's look at an example here. So here we're given that TRY is congruent to ABE. So they're saying that these entire angles are congruent to each other, right? We're told which rays are trisections, trisectors, right? So again, these blue rays are trisectors. And we're trying to conclude that TRW is congruent to CBD. So TRW congruent to CBD. How do you do that? Well, once again, right? A good sign that you use these properties is it's a double use of trisect. In this case, yeah, there is a double use of trisect. So now you've narrowed your options to multiplication and division. Which one is it? Is it multiplication or division? Well, think about it. You're starting with a bigger angle, right? Like you're starting with TRY and you're ending with TRW. If you go from big to small, I just mentioned earlier, that's going to be division, right? So once again, you know it's going to be division property. And now that we kind of map that out, let's write the steps down. So of course you write the given first. Uh, we have 3 givens here. And because we already have all the information we need in the givens, right? We have shown, we already know that there's trisectors involved. We know that a specific congruency is established. So what we can do now is go to the final step, prove that those divisions, right, those smaller parts are congruent to each other. And the reason is the division property. Now, in this problem, you might think like, okay, well, TRW is kind of it kind of looks different from CBD, right? Because it's not uh, exactly like here, right? Um, that doesn't matter, right? As long as uh, these are trisected, right? The like divisions are always going to be congruent, right? So it doesn't matter if the angle is here, here, or here. Um, it just matters that they're congruent to each other. All right, you can look at this problem, right, with this given information and try it for yourself. I have the answers right here if you want to see, but I won't go over this. Okay, let's look at this one now, right? Assuming you have looked at it. So you have angle 1 is congruent to angle 2. So again, I like marking my diagrams first. Then we have these two rays that are bisectors. So PE is a bisector of APN. So PE is a bisector, and they tell us that NE is also a bisector. So we have that's a bisector and this is a bisector, right? Uh, Once again, it's a bisector of this angle, that's a bisector of that angle. We have to prove that XBE is congruent to E and Y. So XBE is congruent to E and Y. Initially, this might seem a bit confusing because you don't know exactly how to prove those two are congruent. Um, but once again, whenever you're given stuff in the problem, think about what you can justify with just that, right? So let's write our givens down first, right? Of course, angle 1 is congruent to angle 2. We have PE is a bisector. I remember, right, I use the acronym sometimes, like BIS, um, just to kind of save some time, right? So useful just, sometimes they might have tests and it's good to just save time when you're doing these long proofs, right? So again, these are all given. So now, well, what can we conclude from those? Well, we have angle 1 is congruent to angle 2, right? But you'll notice that PE, APN and ANP, right? APN, ANP, they are located, if you look at the straight line, they're supplementary to angles 1, right? And this one here is supplementary to angle 2. So once again, I would make that following step and say that angle 1 is supplementary to angle APN, right? Angle 2 is supplementary to angle ANP, right? Those two, right? Remember, if two angles add to a straight angle, they are supplementary, right? I'm just looking at this, right? We've proven that we already know angle 1 and 2 are congruent, and they both are congruent to these angles. So therefore, right, we can conclude that angle APN is congruent to angle ANP, right? Reason is, um, if two angles are congruent to, or it's not congruent, if two angles are supplementary to congruent angles, then they are congruent, right? Congruent supplements, remember? So now what we have done is proven that APN is congruent to ANP, right? Once again, that refers to APN here and ANP here. Why is that important? Well, think about what our end goal is. We're trying to prove that those two angles are congruent, right? XPE and ENY. XPE, ENY. We've proven that these are congruent, right? And we know that they are bisected, so we can of course use properties we learned in this lesson, right? If we're trying to prove that this angle is congruent to this angle, Well, think about what we already know. We know angle 2 is congruent to angle 1. So all we need is to prove that 3 is congruent to 5, right? And of course, the results are going to be congruent, right? Because of the addition property. So to prove 3 and 5 congruent, well, that's just the division property, right? Because here we have two bisectors, right? And we have that the entire angles here are congruent. So we can use the division property. So once again, you can say angle APE is congruent to ANE. The reason is, and I would encourage you to write the entire theorem down, but for the sake of this problem, I'm just going to put division, right? Division property. Now that we've written that down, APE is congruent to ANE, right? We can actually make our final step here. And if you're not sure why, well, right, look, we proved that angle 1 is congruent to angle 2, and we just proved that these two angles here are congruent, right? Well, if you add these purple angles and those angle 1 and angle 2, right? These ones, well, you'll realize that that gives you our conclusion, right? That gives us this entire angle is congruent to this entire angle, which is what we're looking for, right? So once again, we can make that conclusion. Angle XBE is congruent to angle E and Y because, once again, I'm not going to write the entire property here. I'll recommend you do, but um, the reason is the addition property for angles, right? If congruent angles are added to congruent angles, the sums are congruent. So yeah, that's like a combination of division and addition in a proof, right? The most important thing, again, I can't stress this enough, is to look at what you have in the given information and just start solely from what you have there, right? So in this case, uh, with that information given, right, and the diagram, we were able to deduct that um, there would be a division property used at some point, right? Um, and again, a good sign of that is these two bisector keywords here, right? And once you have done that, make sure you sometimes look at where you're trying to improve so you know where to head right next in the proof. In this case, right, we realized that we can just add these two angles to get to our conclusion. So yeah, um, hopefully that made sense. But if you have any questions about this, please leave it down in the comments, and I'll see you next time.